Okay, let's talk about some pointers. So pointers pretty much add a whole new category of data types to our repertoire. Let's look at, let me share the whiteboard. Okay, so you declare an int, something like this, int my value is equal to 10, right? It's our standard variable declaration and assignment. To declare a pointer, we're going to say int star. Now, a pointer is not only applicable to an integer, it's applicable to any data type. You can do it to a double, you can do it to a string, you can do it to any sort of object or class that you create yourself. Yeah, in fact, those are very important so that you can allocate them properly, and we'll talk more about that. So here's our int pointer. I'll just call it my pointer. And what are we going to assign that to? Well, if we don't have anything to assign it to right at the moment, if we're not using it right away, we can assign it to a null pointer. This is new as of C++11 and on, but a null pointer kind of signifies what it says. You're pointing at nothing. I'm not sure, I don't think it's almost like pointing at zero. You're not pointing at anything. So that's kind of what we have set up there. Now, if we want it to point to something, in this case, we have a value, an integer value there, so we can have it point to the address of my value. Okay, so this is a new operator for us, this ampersand. This is taking the address of something. What do we mean by that? So let's see, let's draw our memory. Okay, so let's say this is our main memory. And somewhere in main memory, we have our, whoop, come on, let me draw it. Somewhere in main memory, we've got our, let's see, let's say this is at 0, 6 AD. So that's the actual byte location of this memory space here. And we are going to, in that memory space, for us, oh shoot, I forgot what the number was. Okay, let's call it 06AD0. And for us, in our program, we know this memory location as my value. And what's in my value? Well, right now we've got 10. And that's just sitting somewhere in our main memory somewhere. Now we declare this integer pointer. And that's also going to be sitting in memory somewhere. Everything has to be sitting in memory. And this is also sitting at some memory location. We're going to say 08 DDF for fun, because that's just so much fun. Okay, and this is my pointer. Ah, come on. Okay, move that over a bit. Now the question is, so for a regular integer, we can hold an integer value in it. For a pointer to an integer, we can hold the address of an integer. So what's going to go into my pointer after, oh, I see where that's, okay. Sorry, I didn't realize that was changing from the ampersand. Still did it anyway, don't do that. I'm gonna let it do that. Okay, we're not gonna worry about that, but it should be an ampersand there. So what is gonna go into the value in my pointer in its memory? Well, it's a pointer, it's going to point to my value, so it has to hold the address of my value. So this is in essence saying that this location in memory is pointing at that memory location. So if we actually want to go ahead and use my pointer, or get the value out of it, get the value it's pointing to, you know, if you just printed out my pointer, what do you think this would give you? This would give you zero hex, or hex 6AD0. Is that useful? Does that mean anything to anybody? Well, it means something to the computer, but not too much to us. To actually get the value that it's pointing at, to get 10 out of our pointer, you need to use the dereference operator, which is the star. This will give you back 10. The dereference operator is doing, is sort of undoing the pointer, if you will. It's saying, okay, what memory location it is? Okay, let me go find out what's there. Let me go get what's in that memory location and bring it back. That's what the dereferencing is. So we did dereferencing, but we also introduced addressing, is with the ampersand up here. If you took the address of my pointer, what do you think you're going to get? Well, we said that my pointer is sitting at 0x8ddf. So that's what you would get out of it. You actually get the memory location where my pointer is sitting. And that's what it means to take the address of it. You want to get the address of that variable. Well, should we make sure this all works in code? Let's take a look. Let's go to our code block. Okay, so we have similar code here. We've got int my val equals 10, and then we're setting int pointer, my pointer, equal to the address of my value. Okay. Then we go ahead and we print out my value, which from all of our earlier work, we should know that it's going to be, or we really hope that would equal 10. My pointer is going to be whatever that memory location is that my value is sitting at. And then if we dereference it on line 12, again, we should get the value of 10 back. If we take the address and print out the address of my value, it should be equal to my pointer. So this should be equal to the address of my value, because that is what we set it to. And then finally, if we take the address of my pointer, what are we going to get? Well, we're going to get another memory location. It should definitely not be the same memory location as my value. And it's going to show you where in memory my pointer is actually residing. So let's compile this. Or not, since code box is currently in a bad state. Control save. Okay. Currently compiling. Let's abort. It's not letting me abort. Okay, let's just close it down. All right, well, that's thinking about that. Let's go back to this. So why do we introduce pointers? Well, the Zybook talks about how we can use pointers to come up with more dynamic data structures. In the past, we've looked at arrays. And arrays are contiguous in memory. It means they're sitting, whoop, I can't draw straight. They're just sitting one right after another, right? If this was an integer array, then this is going to be, let's see. This is going to be some offset plus 0 to get our first element, and then some offset plus 4, and then plus 8. Because an integer is 4 bytes, so if we were looking at the byte address of these, it would be 0, 4, 8, 12, 16, 20, 24. And that would be added to some offset. Let's see. We can make up our own offset here. Let's say, oh, lovely. Don't do that. All right. Let's say we're sitting at 100. Then this location in memory will be sitting at 100 plus 0. So still at 100, because that's the beginning of our array. If we had, and then 4. So this location in memory, so this location in memory is 100. This one would be 104, 108, 112, because it's contiguous in memory. These are sitting right next to each other. The problem is if you want to start deleting or adding elements in the middle, this is a lot of work. Everything has to be shifted up or down if you're going to add another element here. If you use a different sort of structure, one that's commonly used is called a list. Instead of having everything sitting right next to each other, you can have a pointer pointing at, yeah, let's see if we can see how good my drawing skills are. And I should draw these together. No, don't do that. Don't do that. Okay. So instead of having everything contiguous in memory like we did with our arrays, which is up here, now we're going to have a pointer pointing at one element to the next. So we could say, so if this was an integer array above, we would have a pointer, like you could have a class or a structure that has class node. And I'm going to make this really brief. So public int value. And then we're also going to have a node pointer. And that's next. Okay. So this node structure here will allow us to create our list. Or I should say this class structure, this object. And I wish, here, let me select that. I should have done it this way. Okay. So when you create one of these nodes, it's going to create two members, the node pointer, next, and an int value. We're going to say that the top of this structure I have here is our node pointer called next. And the bottom part is our value. So value could hold, this could be our 10 value again, right? And we could have had a 10 up here too. Okay, so this is actually, and let's say that this is at memory location 200. And when we create our next node, okay, sorry. So this to start with is actually going to be null pointer because we have nothing to, if we have only a single node, we have only a single node in our list that we're creating here. So pretend these aren't here yet. There's no next pointer to, there's no next node to point at. So we set it to null pointer. It's sort of our holding space, or like our empty string. We're going to set it to null pointer. There's nothing to point at. When we add this next element onto it, then we have something for it to point at, which we're going to say this is memory location, I don't know, 4A5. So to make it point at it, we're going to set it equal to this new node value, which means that our null pointer will be replaced with 0 hex 4A5. Now if we were doing our second value, let's see, what's our second value going to be? I don't know, 60. If we're going to put our second value here, also 60. And we can keep building up our list this way. Keep adding. So this one should now be set to null pointer because we don't have a third element yet. When we add a third element, then we set it to the pointer. If we were adding the element here, we'd just put it in the next array location. You know, this is 0, 1, 2. But now the problem is, and this is a very limited example, if you had hundreds and hundreds or thousands or millions of items in your array or your list, and you suddenly wanted to add a new value in at location, at this second location, for your array, you're going to end up moving everything down. Whatever's in 60 has to move to the next location. Whatever's in that location needs to move, and it just cascades all the way down to the end of the array. And that can be quite expensive to do for an insertion. In the case of our list, the insertion is very cheap. Let's say we wanted to make, let's say we have a node with 40 in it. And we want to put that as the second element. We actually don't want it to be the end of the list or the array. We want it to be the second one. Well, the operation to change that to the second is very cheap. All we have to do is update this pointer to now point, oh, that is not what I wanted. We have to update this pointer to now point to here. Apologies for the arrow. Now, if we know this memory location, let's say it's 0x672, all we have to do is go in and set this equal to 672, and the second item in the list has now become this element, versus the array where we're going to have to move 60 over, but before we can move 60 over, we have to move whatever was in 60's location to the next one, and so forth. Okay, so that's one reason pointers are very useful. It gives you a lot more flexibility over the structure, over the allocation of where things reside in memory. It also introduces to us a new memory space called the heap. So let me save this, and let's clear this. So if we go back and look at our main memory again, main memory has, from a C++ perspective, most of the time, main memory is divided into 4 areas. So this is our complete main memory. We've got 4 different areas. Okay, this first area is sometimes referred to as text space. And text space means this is where the instructions go. Once you compile your code down, it goes into byte format. This gets loaded into main memory, and the program counter, which is kind of like a pointer, points to the location and where you are in the code, and that's going to be in this text area. You don't really need to know. It's good to know that it's there, but you don't really have to know much about it. You're not going to have to modify this. The only time you'd start looking at it is when we get in, if you got into some very deep debugging and you need to step through the code and inspect the code in a very detailed way, try to figure out where the program execution is jumping, things like that, then you would need to look at it. But for our purposes right now, I just know it's there. The next section we'd have is sometimes referred to as BSS. I forgot what Books called it, something else, but it's your global global scope. So any variables defined in the global scope are going to sit here. And again, it's good to know it's there. You really don't have to worry about this too much. Sometimes the compiler uses to optimize things if you have static variables and things that try to place it in the global scope, or if you have a string literal that's used several times, sometimes the compiler can be smart enough to just create one copy of it and have everything point to it. That's kind of what's happening in the BSS. Again, not something you're going to have to worry about too much. These last two areas that we're going to talk about, so the stack is actually the memory that you're familiar with right now. I kind of think of this as like the working memory. This is where the program is sort of living. When you declare a local variable, it's going on the stack. Any variable you declare in a function, that's going to go on your stack. When you're returning back and forth out of functions, that's all on the stack. It's all done on the stack. So that's kind of the memory you're used to right now, or the memory we've been using for the programming so far. So today with pointers, we're introducing a new area of memory, and this is known as the heap. And how you access the heap is with new and delete. These are new operators for us. Now, one thing when you're working with your stack variables, the stack, once you exit the current scope you're in, the stack variables all go away. And actually, partly the reason that is because it is your working memory. We have to make sure that the stack isn't getting too big so that we have memory to play with, memory to work with, memory for everything to execute in. If you need something that's going to be permanent, that you want to transcend the current scope, you would put that in the heap, and you would do that by calling the new operator. Another really good reason you would use the heap is the stack is actually limited space. It's defined differently on every platform, but your stack is in the order of megabytes. You know, it could be 2 megabytes or 6 megabytes or 8 megabytes. Linux, it's typically, I think it defaults to 8 megabytes. But once you run out of stack memory, if you go outside of the stack memory, things start going haywire. You're starting to go into either usually the stack grows into the heap. And if you have things, if anything's been allocated on the heap, the stack is going to start clobbering those things and just undefined behavior and bad news. So typically the heap is a lot larger, bigger area that you can allocate larger objects. You can allocate a lot more objects. And your lab talks a lot about that. So it's definitely a good topic to understand. Okay, so let's talk about allocating to the stack in the heap. code. So we had our node earlier, our class node. Let's put that in here again. And in there we had node pointer next. And we had int value. Now if we're in our main, we can instantiate our node class. We can say node, my node. Now, if you declare it like this is going to place it on the stack. So for our example here, so my node is going to be here. If we go ahead and say node pointer node, sorry, it's not called pointer node, heap node equals new node. Okay. Now we've introduced the new operator. We're using the new operator. Guess where this node is going to go? It's no longer going to be on our stack. It is going to be on our heap. Okay, so in 2 different locations. Now, another not fun intricacy of using the heap. So, like we were saying, our local variables on the stack go away when we leave the scope that we're currently in. So we're in the main scope right here. We created my node on the stack. We created heap node on the heap. When main exits, when your program ends, when this program ends, my node, the memory for my node will be returned to the system because it's on the stack. What we have here with the heap node is what we would call a memory leak. The heap node has been allocated on the heap, but it has not been deleted. If you knew something, you're explicitly asking for memory, you explicitly have to release the memory as well. You need to delete it. This is not necessarily the case for every language. It is the case for C++. They don't do anything that's referred to as garbage collection. If you no longer are using a pointer, the system doesn't care. It still keeps it there until you tell it that I no longer need it, to delete it and to release that memory back into the pool of available memory. So once you leave the scope of main, my node will go away. Poof, it's gone. Heap node will not. How do we get it to go away if we don't want it anymore? we call the delete operator on it. This will release the memory back to the system. Are memory leaks good? No, you do not want memory leaks. This is what Windows is notoriously bad at. Why you used to get the blue screen of death all the time, because they had memory leaks everywhere, and if you ran it long enough, eventually you use up all your memory and it becomes unstable and crashes. Memory leaks bad. This is one of the reasons that C++ is very powerful, because you can do these new and deletes explicitly on the heap. It makes it very fast. It also makes it incredibly difficult to program without memory leaks. It makes it a much easier language to shoot yourself in the foot with. So, so aren't you all glad you're taking C++? Yes. So kind of the rule of thumb is for every new you have in the system, you should also have a delete call. And sometimes a really nice way to handle that is to actually do it all within the class that you are dealing with. So if we look at our node class, actually the node class is a bad example. We can't do it with the node class. But let us say you have a class data node. And your data node has string metadata. And that's going to describe your data. And then it also has a data array. And the data maybe has 100 bytes in it. Okay. Well, if you created a lot of these data nodes on the stack, eventually you're going to run out of stack and it's not going to work anymore. So what you want to do because this is large, one thing you could do is in your constructor for data node, and this is going to be somewhat pseudocode because I'm going to run out of space otherwise. You can say data equals new int array of 1,000. Now this doesn't compile syntactically because this array now would become, it's not an array anymore, it's a pointer to data. And then once you enter into your constructor, you will actually new the space for that data. Now, we already talked about last section with our classes, destructors. Here's where the destructors come in handy. You code up your destructor for data node, and within it, you are going to delete, and you have to use the delete bracket operator, square bracket operator for an array. You're going to delete your data. So why is this a nice model? By the way, don't forget about your copy constructor and your assignment operator also. Those are also ones you would have to deal with if you're dealing with pointers in your data node. Sorry, if you're dealing with pointers in a class. That's, again, looking at the last section in this chapter, talking about the rule of 3, that's what it's referring to. The rule of 3 is if for some reason you need to create a destructor, a copy constructor or an assignment operator, you should actually define all of them. In this case, I'm defining the destructor because we need it to deallocate the memory. So then you would go ahead and also look at the copy constructor and the assignment operator. Okay, so I'm going to delete the data in here. And the nice thing about this is anytime the data node constructor is called, the data is going to be allocated appropriately. And anytime the data node destructor is called, it's going to delete the data. If I have a data node in my main that I have allocated on as a local variable on the stack, the data node itself will be on the stack. The data node will be here. But this very large part, the 1,000 integers, which is like 4K of data, is actually going to be allocated on the heap. And when my data node leaves the scope of main, the destructor of the data node is going to be called, and this data node destructor will run, and it will delete the data for me. If I create my data node and it's on the heap, this will go ahead and create the data for data node and create the data array, new it, put it on the heap. Then when I call my node, when I call delete on my node, this delete on the data also gets called. So there is a programming idiom which says that you should only new and delete memory within constructors and destructors. Well, that's a really nice thought. I have not found it terribly useful in practice, but it's a good idea to try to keep the news and the deletes into your constructors and destructors. Okay, so point is, for every new, you need a corresponding delete, and putting it in the constructor and the destructor is a nice way of making sure those pair up if possible. Of course, if you're declaring my node on the heap, you still have to call delete for my node to get this to run. Okay. So with that, I think we're going to call it. We have let's quickly walk through the lab write-up. If my word is cooperating. Okay, pointers lab. This is a little different structure than the ones we've had previously, so just kind of keep that in mind. Learning objectives, heap memory allocation versus stack memory like we talked about, pointers versus an object, pointer dereferencing, memory addressing, memory leaks, constructors, destructors, copy constructors, and assignment operators, and the rule of 3 corresponding to our destructors, copy constructors, and assignment operators. So we're going to take an in-depth look at pointers. This lab has 2 parts to it. The first part is you're going to get, later in the lab, it will give you a set of questions. And they're questions that you're going to do a very small amount of code, probably like a line or two of code, and then run it and see what the answer is that you get out of the program or the compiler. Please submit the answers to these questions in the comments in the top of main. If you look at the main.cpp you have, it already has numbers iterating which questions you need to answer. So it should go from, I think it's like 1 to 13. There's 13 questions. And then there's a step 14 in the lab to get your program back to the original state it was in before you started answering the questions. Once you're done with all those questions, you need to fix the application. When you first build and run the application, it's broken. It shouldn't work. If it does work, then you have a huge stack. Okay, so the lab includes an abstract data type of a photo and a passport. So passport is going to contain a photo, kind of like your passport, if you have one, has a photo in it of you. We're going to have a passport class that contains a photo within it. And photos tend to be very large chunks of data. I gave an example, just kind of a rough example here, a 4K image. One of the resolution sizes on a 4K image is 7680 by 4320, which comes out to, over, let's see, what is that? 33 million pixels. That's a lot of data, especially if you look at 36 bits per pixel. It comes out to almost 149 megabytes. 149 megabytes is pretty huge. You're talking about a gigabyte with, oh my gosh, why am I making myself do math? In under 20 pictures, you're going to be over a gigabyte of data. In this class, in the photo class that we're dealing with, we have the size set to 16 kilobytes, which is probably unrealistically small at this point, but they're tiny little passport photos. So the application is going to try to allocate, or sorry, not allocate, but it's going to try to create many, many, many passports to process. And then you have to see how the program responds and try to figure out how to fix the program. But do the questions first. Hopefully those will help you give you more understanding and insight into pointers and how they're working. And then based off of a lot of that information, go in and try to fix the application. So, pointers lab.zip has the 5 files, the main program, which the main program has the location for your lab answers at the top of it. Please use that. If you don't put it in there, I'm not going to know where to look for the answers to your questions. Please do not submit any sort of Word or other type of document. Just keep it in your main.cpp. Again, our same compile line, and then rubric at the bottom. So in this lab, unlike our previous ones, you're going to get 13 points for all the questions you answer correctly, or you can get up to 13 points, 1 point per question. And then 4 points. So, hint, hint, hint. To fix the program, I'm expecting you to implement a destructor, copy constructor, assignment operator, and modify the constructor for the classes that were provided. If you get the application working, that's another 3 points. 4 points for just implementing and modifying. You don't want the code to leak memory. I'm going to take points off if you're leaking memory. I'm also going to take points off if you modified main.cpp. I want you to put the answers to the questions at the top of it, but the code should not change. If the code to main.cpp changes to fix the application, 5 points off right at the top. So don't do that. So, all right. Well, I hope you enjoyed this lab. I had a fun time writing it up. and let me know of any questions. All right, everybody have a good night.